Kmiecik is going to tell us about Async IO.
Hello everyone, I hope you hear me okay. So a few words about myself. My name is Paweł Kmiecik. I work as a senior software engineer in machine learning at DeepSense AI, and I'm also a co-founder of PyData Bydgoszcz. So agenda for today. We all agree that Python is not the fastest language in the world. But to understand how we can make it a little bit faster, we need to divide tasks to two groups, which are CPU and IO bounds. Then we go into basics of Async IO and its building blocks. One of them is coroutine, but to understand it, we'll go back in history to generators. Then we'll talk about coroutine event loop, some constructions of Async IO, and then we'll compare it to threads. So first we need to understand that concurrency and parallelism are two concepts which are similar but not the same. Yeah, parallelism is to deal with CPU-bound tasks, while concurrency is to deal with IO-bound tasks. What are CPU-bound tasks? Well, if you have some heavy numerical computations, you may try to split it into more and simpler tasks and send to your CPU cores or even different machines, right? While IO-bound tasks are different in this way that IO operations are much slower than CPU tasks. It's like 70,000 times slower. This is a magic number that I remember from some book, but I don't remember which one. And today we're going to take care of IO-bound tasks, because Async IO is a module which will help us speed up IO-bound tasks more likely. The thing is that sometimes the way, maybe the practical way we are solving those two issues, so to parallelize or to make something concurrent, means practically the same, which is, for example, a case in Java. Yeah? We are using threads there, and they can be just sent to different CPU cores, and we achieve parallelization the same way. But this is not the case in Python. In Python, we have something which is called global interpreter lock, and it holds the interpreter consistency. There were many tries, at least few tries, to get rid of this thing because it limits our parallelization capabilities in Python. But they weren't successful, so we have to live with that thing. So if we have this limitation of global interpreter lock, whether threads are still useful to something, the answer is yes, and they are useful for IO, but useless for CPU-bound tasks. The reason they are still useful is that IO operations are releasing this global interpreter lock. And because IO operations are very slow, it's not a big problem that we don't use the full potential of our CPUs and our cores. So if we have the solution for IO-bound tasks in Python, which are just threads, so what's wrong with them? And the answer is CPython is using system threads. And as you probably know, I hope, systems threads are much lighter than, for example, system processes. But still, they are introducing some overhead. Context switching, I mean, when your system decides that one thread should be replaced by another one on a core, this is context switching. Also, the system might decide to switch threads not in very optimal moments. Also, it do some harm to processor optimizations like caches and so on. And also, the Python thread object need to communicate with system threads. So it all introduces some overhead, some anti-optimizations into our code. And what is Async IO then? So this is an alternative approach to thread-based applications. Also, it introduces a new paradigm to our coding. You probably know structural paradigm, object-oriented, functional, and so on. And Async IO introduces something which is called asynchronous programming paradigm. You might know it from, because it's not something very new and new only in Python. You might know it from, example, JavaScript. The whole node is working on that, yeah? It's single threaded. And the reason it's worth using is that it's using non-blocking I/O operations, which are just faster. Of course, it requires the operating system to support such operations, but what we do not have here, we do not have context switching, so preemption, because everything is single-threaded. Everything works on single thread. And main building blocks are coroutines and the event loop, which controls those coroutines. Yeah, so that's the, let's say, theory. And as David Beasley said, it's not well documented, but this citation is pretty old. So these days, there is a lot of Python Async IO tutorials on the net, and after all those years, we live with this module. We could expect that all Python developers know it and use it, but my particular experience is much different. And I'm doing a lot of recruitment interviews, and when I have a really nice candidate who even knows how to make parallel or concurrent programs in Python, then it's most likely that he or she does not know Async IO. That's why I'm here. So maybe a question to you. Have you ever used Async IO module? Hands up, please. Whoa, nice. Yeah, so this is much different from my experience. But I hope that what I tell you today will help you understand it more deeply. Yeah, so what is this magic that all those Python developers are so afraid of, or is something not very understandable? The concept of coroutine, yeah, so, and I don't want to critique anyone, because I was one of these guys some years ago. That was something strange, and I didn't know for what can I use it. So we'll try to disenchant this coroutine thing. But to do this, we need to get back a little bit in history. And I will show you something that you probably don't know about generators. Here is the example, very simple example of generator, just to recall how it looks like. Yeah, so we have this special yield operator or yield word, and this makes this function is a generator, right? Very simple. Here is another example. And this is very, I would say, this generator does not do anything useful. But I wanted to show that there is something like yield from. And this statement is just taking values from a generator and yielding them again. So it's like a syntactic sugar. We don't need to write our own for loop in this data from first source generator. We have this yield from, and we have less boilerplate. But still, it's just a generator, a lazy iterator, that, as we know those generators. And here is something that probably, I hope, a lot of you don't know about generators. Sorry. So here you can see that yield is placed at the right side of assignment operator. And also at the right side, there is something strange with this generator. I'm initializing it with next, and then in line 16, I'm using a send method of a generator. So this is something I count most of you don't know about generators. Yeah, this is this emphasis of this. And also, we can even use return statement in this generator. It is rather less likely to meet in normal code. And the way we are getting values from such a return statement is not so straightforward. We need to take it from stop iteration exception object in value attribute. Yep. But here you can see that with generators, we can communicate them in two sides. Yeah? Not only generator is producing something, we can send also something to a generator. And here is the last building block of a coroutine. So I just added from the previous example, I added a cancel exception here. And here you can see that I added try except block to my generator. And also there is another method on a generator, which is throw. So I'm injecting the exception inside a generator, which will just interrupt its instructions immediately. So these are the main building blocks of coroutines. Of course, today they are not. We are not using them as generators, but some years ago, coroutines were based on generators. And here you can also see that we have everything to have two-side communication with some abstract object, which we then call coroutine, and also we can cancel this coroutine. So we can imagine that a coroutine is something, or can be something, which will pass steering from a caller to another generator, for example. And it works in two ways. And also we can retrieve some values from those generators. And this is a simple example, but normally we can have a lot more delegating generators, sub-generators, and so on. So it might be much, much longer. And yeah, and this is how it looks, how it looked a few years ago. So to create a coroutine, we just needed to use special decorator. But what is important, and also it's visible here, yield from statement was very useful because it was used to pass the steering from caller to a generator to another generator and so on. Yeah, so this is how this old style coroutines looked like. Maybe some of you are old enough to remember this. And how it looks like today? Well, we have some syntactic sugar. So just to define a coroutine, we are closing all this mechanism inside an async def statement, and we replaced yield from with await. And of course, when Python is being developed, those two concepts, I mean generators and coroutines, might diverge because of this different syntax. And they have diverged, which will be described later. But for us, it's, I think, much easier to think about coroutines as generators, which are just passing steering with yield from. And of course, those strange exceptions as well. Yeah, so the history is pretty old in terms of how those coroutines was developed. And those send, throw, and close also methods were introduced in Python 2. In Python 3.3, we have those added return and yield from, and starting from Python 3.5, we have this modern coroutines defined with async def, and we see awaits rather than yield from. Yeah. So the differences between old style coroutines and those new style coroutines are mainly, this is just a syntactic sugar, but it lets introduce asynchronous iterators and context managers. And it's now easier to still think about generators like a classical lazy iterators. Of course, the send, close, and throw methods are still there, so you can imagine some much more different and strange usages of those methods. Maybe they will be genius. But we can get back to thinking about generators like lazy iterators. And also we have some nice warnings when, for example, we forget to await a coroutine. For example, that's not the case in JavaScript, when if we don't await the coroutine, it will just be fired, but without control. In Python, it's required to await a coroutine to just run it. Okay, so we have these coroutines as we can think of them like generators on steroids, let's say. But who is the caller? So the caller, so the object that controls everything and decides which generator or coroutine, never mind, is being run at the time, is event loop. So this is one of, let's say, the second of basic concepts in Async IO. So when we see in the code the await statement, the steering is given back to the event loop. And we can imagine that if we do some HTTP request, we are awaiting its result, then the steering is get back to event loop, and event loop can decide to run another HTTP request, for example. Yeah, so there is no active waiting as it is with blocking IO. And as I emphasize one more time, everything is done in one thread, so no context switching. Yeah, this is my own art, let's say. And I just wanted to visualize how you can imagine how it works underneath. Yeah, so every await can just mean take another task, task and just run it. I won't get into the details how this event loop chooses the task, because for now I even don't know it. But we can think of it for simplicity as it's kind of round robin with some queue or something. Yeah, so we have defined coroutines as not lazy generators, but not standard generators, yeah, and generators that have not standard capabilities. But today we have the syntactic sugar with async statement, and how those coroutines are, let's say, organized inside Async IO. So coroutines are wrapped with objects which are futures, but futures are, let's say, designed for library and framework developers. They are low-level structures, and we as standard coders shouldn't use them. For us, the object that we should use is task. So it has some high-level access, it wraps the coroutine, and also can be cancelled in easy way. But we know that under this cancel method, there is some exception being injected into some generator. Yeah. So if we compare Async IO to threading, we cannot say that we are getting rid of all the problems of concurrent programming. So we still need critical sections if we are operating with some external resources, for example. So Async IO have its own version of logs, events, conditions, semaphores, and so on, all those synchronization primitives. Also has queue for communication, but we need to remember that they are not thread safe, because if we are using Async IO the right way, we do not use threads, which is not always true, but we'll tell about it later. Yeah, but in general, they are not thread safe, but we need them. So comparing to threads, Async IO has just better time performance. There is no GIL, so there are situations when if we would develop something using threads, we would need critical section and logs. Why at the same time we wouldn't need them in Async IO? Also, we have full control over execution flow, because we know when our coroutines might be interrupted, let's say, and it's only when we see a wait statement. Yeah, it won't be interrupted somewhere between. And but we also need to remember that there is some slight memory overhead, because as coroutines are generators underneath, they need to hold their state. Yeah, so they can't be just picked up by the garbage collector, right? They need to persist in memory until we need them. Yeah, so I have a live demo, but it's a recording, so more like a dead demo. And I created an application just to compare something. And this is the sequential example. So my application downloads images with cats. I won't show you everything. It's available on my GitHub, so you'll be able to check it. So the sequential, so it's not parallelized, it's not made concurrent, it's just for loop. Took like 6 seconds. Sorry. Here is the code, and we can compare now how we can do it with threads and with Async IO. In threads, I'm using just requests, and in Async IO, some standard libraries for HTTP requests is IO HTTP, and you can see it also with some asynchronous context managers, so this async with. But in general, the code is very similar, only those async statements are something maybe strange. And also here is the blocking download cat code. and the Async IO version. And what also is important here, I told you that if you do it right, you don't need to use threads, right? But let's say Async IO has some workaround in situations when you have to use blocking IO because, for example, you don't have library, the right library for your strange database, for example. That was the case in one of my projects. What can you do then? In Async IO, you can simulate that something is asynchronous by sending this blocking thing to a thread. So unfortunately, we still need to use threads in some situations, and you can do it with run in executor. Yeah, so there are ways to just work around such situations. And here is the example with the last, let's say, lines of code when I'm using futures thread pool executor, and there is this submit statement, and I'm using futures as completed, so the results are coming in the order of completion. Yeah? So it's not order of this list, but it's order rather random of completions. And let's see how it works. Yeah, so this is a blocking code, yeah? And the alternative is using executor map, which will save this order, but I'm checking it with as completed, and you can see here also that I'm using 3 workers. Yeah, the speed is better, but not so great. Let's play a little with max workers parameter. With 12, it's 0.5 seconds. And I played also with some other values, 378 milliseconds. So, and this is the way we should pick this number of threads empirically testing on a given environment. 50 is probably something too much. Okay, but we've seen the best results was like 370 milliseconds. And here is the asynchronous version of it. But I wanted to show you that is very similar to previous example. So if someone is used to thread pool executors, the API is maybe not always, but it is rather similar. So I'm also using as completed, but with Async IO, not any threads. And I'm awaiting this future object. And let's see how it runs. And also, I'm using Async IO run. Yeah, of course, there are some differences, but yeah, so this is my async function with as completed. Here is some wrapper to my time it decorator just to work. But the results is just better. Of course, it proves nothing because it's just my laptop on not, let's say, laboratory conditions and so on. But I repeated this a lot of times, at least 3, because this is my third presentation on this. And the results were always the same. Yeah, and I haven't shown you the full code. If you'd like to check it on your own, you can just go to my GitHub. My user is Tenzo, and find this repository. So, and the last tips, I highly recommend checking out this repository. It's awesome, Async IO. It's just a growing list of Async IO compatible frameworks, libraries, and so on. One of them is Fast API, which I just love, and some tips for because I'm an ML engineer, so and creating backend services for standard use cases is just nice with Async IO, but in Machine learning inference services, it's sometimes not so easy. And my main tip is just never block the event loop of Async IO. So chop your code with awaits, but maybe a better solution would be to run in executor. Yeah. So, yeah. Or just use a framework like FastAPI and forget about everything what I just told you. Yeah. Thank you for watching. Highly recommend to visit our PyData Bydgoszcz YouTube channel. You can also contact me on LinkedIn. And thanks.
Great, thank you very much. We have some questions coming up. So the first question is, could you repeat the part when you said things about generators? Somebody did not understand exactly.
Yeah, it's hard to understand because normally we think of generators like lazy iterators, and it's the right answer. And here is this let's say, visualization, how we should think about this. So caller, I mean the event loop in this example, is using the coroutines in a way like generators work when we add send, throw, and close to generators. So when a generator, for example, the generator which is doing some I/O operation, and the generator, let's imagine that generator is calling some non-blocking I/O. It must be supported by the operating system, but when at this time the generator is waiting for answer, it just yields something. It's not very important what it is, because it serves only for getting back steering to the event loop. And even if we created a lot of coroutines at the time, all this steering is going back by all those coroutines, like it is here, right? It's given back to event loop with this yield statement. Yeah. Of course, now it's opaqued by await. Yeah, but this is this event loop which is, let's say, placing the first await in this chain. Hopefully it was clear enough, but I know that during a 30-minute speech it might be hard to understand. If someone would like to understand it deeper, I recommend a book, Advanced Python. Yeah, and then it's really clearly described.
Thank you very much. Next question, why is Async IO faster than threads?
It's maybe not always true, so I give some simplifications here. The reason is threads needs context switching. Yeah, so we have some operating system here in place which needs to do some job. Also, the threads in Python requires GIL operations. So GIL is just a lock, and if someone knows the concurrent programming, we should avoid locks whenever possible. But we cannot avoid this one. This is just a global interpreter lock used by interpreter. And also it might happen, of course it's not always true, but it might happen that the operating system will decide to replace your thread with some other thread. And for example, there were some useful data load into CPU caches, but when it's replaced, then the caches needs to be flushed, and if our code goes back to this core, they need to be loaded again. Yeah, and all those operations are giving some overhead, while Async IO working on single thread just don't have it. Yep.
Great, thank you very much. Next question, is testing async stuff any different than sequential?
Yes, it is a little. At least it needs, I'm using PyTest for testing, and it needs some extension. I don't remember if it's already like included in standard PyTest installation, but it needed to at least a few months ago, or maybe years. Time goes so quickly. It needed async PyTest or something like that, and because normally it will just won't work, because PyTest does not know that it should run all those coroutines, because tests of async functions or methods should also be async. They should be coroutines as well. So PyTest does not know it should be run this way. But if we added this extension, it will run all those async tests in an event loop. Yep.
Okay, thank you. Do you use Async IO event loop replacements like UV loop or any IO?
I think that UV loop is a part of Fast API by default. So yes, I'm using, and I don't know the second any IO, but I should probably get know of it.
How would you compare Greenlets and Async IO?
Greenlets. I should probably know more about them. If I remember correctly, Greenlets are used in Java. Am I right? I'm an ignorant here, probably. Yeah. So we can talk about this maybe after the presentation, because I don't remember Greenlets.
Great, thank you. This is it for the questions. Thank you very much.
Thanks.